Welcome to this lecture on functions. In this first segment, we will define what a function is and we will provide some related definitions. So to define a function, first we need to start with two sets. Let's call them C and D and assume they are not empty. Now we can define a function f from set D to set C, denoted with this notation, and say that a function is an assignment of exactly one element of C to each element of D. In other words, a function is a set of pairings that associates to each element of D a single element of C. In this case, D is called the domain of the function f, and the set C is called the codomain. So the function goes from the domain to the codomain. So let's consider an example of a function. First, we need to start with a domain and a codomain. The domain in this case is the set V, X, Y, Z. The codomain is a set 1, 2, 3, 4, 5. Notice the domain and the codomain could be the same. Most of the time they are not. And let's draw the set D with its four elements, represented here with a dot and then a label next to each dot. And similarly, we can draw the set C, the codomain. Now remember, a function is an assignment of one value of the codomain to each element of the domain. So let's assume that a particular element C in the codomain is assigned to some element D in the domain. The notation for this will be to say that f of D is equal to C. Again, the function goes from the domain to the codomain. And in this case, C is called the image of D, and D is called the pre-image of C. So let's see how we represent this for our example. If, for example, f of V is equal to 4. Notice V is an element of the domain, 4 is an element of the codomain. The function goes from the domain to the codomain. And in this particular example, we assume that V is associated with 4, which we represent with this notation. One way to represent this in our graphical representation here is with an arrow from V to 4. Notice again the arrow goes from the element in the domain to the element in the codomain. So in this case we say that 4 is the image of V. In other words, 4 is at the head of the arrow here, and V is the pre-image of 4. In other words, V is at the tail of the arrow. So to define a function, of course, we need to associate to each element of the domain an element in the codomain. So let's associate to X the element 5 in the codomain. Let's associate to Y the element 1 in the codomain. And let's associate to Z the element 3 in the codomain. By the way, this kind of diagram or representation of a function is called an arrow diagram, since the associations of the function are represented as arrows. So the blue arrows here define this function. So in this function, what is the image of Y? Well, you start from Y, you follow the arrow, the image of Y is 1. What is the pre-image of 5? Well, in this case, you have to start from the codomain, find the element 5, and go backward along the arrow and find the pre-image of 5 to be X. Let's consider one more definition related to functions. We call the range of a function from D to C the subset of the codomain C that contains all of the images of elements of the domain D. So in other words, the range is the subset of the elements in the codomain that are images of elements in the domain. In other words, it's the subset of the codomain of all the elements that have arrows going to them. So in our example, what is the range R of our function f? Well, R is a set, and in particular, it's the set that contains the element 1, the element 3, and the element 4, and the element 5. These are the only elements of the codomain that are images of elements in D. These are the only elements that have arrows going to them, according to the function f. Now, let me make a couple more observations. First of all, there are many names for functions. Here we call them an assignment of elements to elements in another domain. I talked of pairings before. Functions are also called mappings or transformations. But probably the most important observation here is that a function is actually a special kind of relation. And in particular, a function from the domain D to the codomain C is a relation from D to C. Now this is important because it connects the concept of function to the concept of sets, which we studied in the previous lectures. Remember that a relation is a special kind of set. It's a subset of the Cartesian product D product C. Well, a function is just a subset of that Cartesian product. In other words, it's a relation. One way to see this clearly is on our example is to rewrite f, the function we're dealing with, as a set of pairs, and the pairs are v, 4, x, 5, and so on. In other words, f is a subset of the Cartesian product of D and C. Notice it doesn't contain all the possible pairs where the first element comes from V and the second element, comes from D and the second element comes from C. In fact, a function is a special relation in which there is a unique pair for each element of the domain. Why is that? Because by definition in a function, every element in the domain must have an image. So when you look at the function here, it must have a pair for V, it must have one for X, it must have exactly one pair for each element, same for Y and Z. If it had two pairs or more for a single element, that means there would be more than one arrow leaving from that element. And if there were no pairs for that element, then there would be no arrow or no element associated to that V. So just keep in mind that a function is a special kind of set, and more specifically, a special kind of relation. In fact, this is so important to your understanding of the big picture in this course that I put it in writing. And I call it the hierarchy of discrete structures. Turns out sets are the most general type of discrete structures. In fact, you could say it's the foundational discrete structure on which most of the other structures are based. So remember, a set is an unordered collection of items. Then a relation from set D to set C is a special kind of set. Namely, it's a set of ordered pairs, or two tuples. And more precisely, a relation is a subset of the Cartesian product of D and C. Now, what is a function then, as we just defined it? A function from D to C is a special kind of relation from D to C, namely from the domain to the codomain. It's the relation that contains exactly one pair for each element of the domain D. Remember, a function is a relation for which there must be exactly one element associated to every element of the domain. So in other words, in a function viewed as a set of pairs, there must be one pair for every element in the domain. Now, later on in the class, we'll talk about sequences, where it turns out a sequence is a special kind of function. It's a function where the domain is the set of natural numbers, 0, 1, 2, 3, and up. So basically, a sequence is a function where the domain is a set of integers. So you got f of 0, f of 1, f of 2, f of 3, etc. And a sequence is basically the same as an array in computer science. The elements of an array are put in order. They each have an index, 0, 1, 2, 3, 4. So you can tell that a sequence is very similar to an array. The main difference is that a sequence can be infinite, where arrays obviously are finite since they are constrained by the amount of memory you have. And finally, a string is a special kind of sequence. Namely, it's a finite sequence whose codomain is some set of characters. Indeed, a string is nothing but an array of characters, and an array is just a sequence. So the point of this slide, and I will finish or conclude the segment on this, is to show you that there is a hierarchy of structures where the set is the most general one, a relation is a special kind of set, and a function is a special kind of relation, and therefore a special kind of set, and a sequence is a special kind of function, and a string is a special kind of sequence. It's always good to have this big picture in mind whenever we dive into the details of one of these structures later on.